Okay, so guys, let's now look at what happens for it if we change the c value. Alright, so what I mean by that is if we have a sine function that looks like this, okay, what happens if we have a value in there for c? Alright, now, what that c is doing is that it's actually changing the angle, okay, or the x value, which usually represents an angle, okay, that our sine function is dealing with, okay? What do I mean by that? Alright, let's draw in a quick table. Alright, let's put in what it normally would be. Okay, so normally we would have 0, pi on 2, pi, like that, okay? Now, let's change that, okay? Let's actually make our c equal to pi on 2, alright? So let's make our function alright? Okay, so what I mean by that is, okay, is let's then stick in our table what our value for x minus pi on 2 would be, okay? So this isn't taking the sine yet, alright? Well, 0 minus pi on 2 is just minus pi on 2. This would be 0. This would be pi on 2. This would be pi, and this would be 3 pi on 2, okay? So basically, everything's just happening, right? It's actually doing what happened before. So if you imagine if this table kept going, right, negative pi on 2 would be here, and that's actually happening here. So it's happening later. Then the 0 happens here, but that happened over here. Alright, so the 0 comes later. Then the pi on 2 comes later. So everything happens, it's just basically a step later. Okay? That's what it actually looks like on our graph as well. So, if we just quickly draw in some values here. Alright? So, everything happens, it just happens a step later. So, for x equals 0, we're actually looking at x equals negative pi on 2. And at that point, our original graph is actually at negative 1. Which means, at x equals 0, we're actually at negative 1 now. So let's go with blue. Alright. Then, at x equals pi on 2, we're up at 0. Okay? What I mean by that is normally, okay, we're up at 1. But we're actually going to represent what happens at x equals 0, okay? And that is actually 0, okay? Then, we move to the next step. So now we're normally looking at pi, alright? But we're actually going to use the value of x at pi on 2, okay? Well, that's at 1, alright? And the idea, guys, is that we get the same graph, okay? But I'll quickly just draw what we normally have, alright? Yes, that's right. Okay, so can you see that it's the same graph, it's just been shifted that way, okay? So you can take any point, alright, and the gap between the same point on the other graph is actually just pi on 2. Okay? Or you can even take, so this point here, alright, the gap between those is pi on 2, and that gap is how much, is what our c value is, okay? So, we move across the value of what our c is here, okay? Cool. Let's have a look at if we change the d value. Okay, so guys, so we're going to look at what happens if we change a d value, okay? So, if we just isolate that, we're just left with something that looks like this. I put brackets around the x just to make sure that we know that the d sort of comes on afterwards. Alright, so sine of x is the function, and then the plus d is sort of adding on the end. It's not x plus d, we don't want to confuse that. Okay? Anyway, let's start with our table of values. Alright? So, Okay, this time let's add in, let's make d equal to 1, so that the example function is going to be y equals sine of x plus 1. Okay, so let's put into our table here, let's just go sine x plus 1. Okay, so at x equals 0, sine of x equals 1. Well, we've got sine of x plus 1, well, that's 1. At x equals pi on 2, sine of x is 1, but sine of x plus 1 is 2. Okay? At x equals pi, sine of x equals 0, sine of x plus 1 is 1. Okay? Okay, and at 3 pi on 2, alright, sine equals negative 1, plus 1 actually equals 0. And at 2 pi, sine of x equals 0 and 1 is just 1. Okay? So, let's plot where these are on our graph. Alright, so at x equals 0, sine of x plus 1 is 1. Well, that's up here. At pi on 2, sine of x equals 2. Ooh, that's all the way up here. Okay? At pi, it equals 1. Well, that's here. At 3 pi on 2, it equals 0, which is here. And at 2 pi, it's back at 1. Okay? So let's play join the dots. Okay, and it will keep going that way, and it will keep going that way. Okay, so what's happened is adding 1 on the end, alright, is we've just grabbed our graph and we've just gone and shifted it up. Alright, so again, let's just put in a dummy graph of what we usually see. Okay, and so on. Okay, so all that plus 1 does is basically take where we are on the graph, alright, and move us up 1. So in between here, it moves us up 1 to there. In between there, it moves us up 1 to there. Okay, so that's all that does. Alright, so let's have a look at an example that combines a few of these all at once. Okay, so guys, the example, alright, I've drawn up a set of axes hopefully close to the same size as the other one, so we can visually see basically the difference that what these things are doing, the difference that they make to the normal sine function. Alright, so our example is going to be y is equal to a half sine of 2x plus 1. Okay, so this value at the front here, so that is basically the a. Alright, that, as we discovered before, affects the amplitude. Okay, so normally our amplitude goes from 1 down to minus 1, alright, the highest value to the lowest value, but because we're doing a half as our amplitude, that's going to come down to a half and minus a half. Alright, so normally we'd go from down here up to here, alright, but that's actually going to narrow down. We're only going to go between those two values. Alright, it's a more narrow wave, okay, than this sort of tallish one we've got over here. Alright, before we draw it in, let's consider though, alright, we've got a plus 1 here, which is our d, alright, and if we remember, that actually moved us up and down, okay, so when we did it before, the whole graph stayed the same, but we moved up by 1 value, yeah, so in actual fact, instead of going from negative a half up to a half, alright, we have to add 1 to that. So we're actually going to go from a half up to 1.5. So what do I mean by that? Alright, so we were going to work in this range, okay, because of this amplitude, alright, that trimmed us from 1 to negative 1 down to here, alright, but now this plus 1 has shifted us upwards 1, okay, alright, this 2 in here, now that is the same as our b here, okay, so that affects our period, okay, so our start value is not affected by that, which means we can actually put that in, alright, our start value is normally 0, okay, but because we've got plus 1, it's going to be up here at 1, alright, now, our period is now not going to be 2 pi, it's going to be the same as the example before, it's actually going to be pi, because by doubling this, we're getting all the values twice as quick as what we normally would, okay? So our up and down period is only going to go from 0 to pi, alright? So the end of our period will be there, okay? So we're going to start here and end up here, alright? and now we just need to basically fill in the gaps. Alright? So we're going to go up, down, and back in that short period of time. And our up is 1.5, and our down is 0.5. Alright? So like that. Okay, where that is 0. Bit of a wonky curve there, but let's pretend that's okay. Alright? So that is one period on our graph, right? And obviously that continues on. Alright, and it will continue on that way, and it will continue on this way. Alright, continues on that way. Okay, so as you can see, alright, the numbers we've included here, which reflect our A's, B's, C's, and D's, alright, have significantly affected, okay, our starting graph, right? So instead of having y equals sine of x, we've got y equals a half sine 2x plus 1, which initially seems a little bit complicated, alright? But we just have to work out what each of these things affect, alright? And apply it to the normal situation, okay? Hopefully that makes it a bit clearer. And yeah, I'll see you in class next lesson. Thank you.